We're going to take a look at a variety of systems where we can potentially know what their potential energy is as a function of where the object in the system is. And so the first one, and also just to be able to understand the behavior of that system and how the energy is switching back and forth between potential and kinetic energy. And so we're going to start off here with a pendulum system. And we're going to see, so if we release the pendulum, and we saw a pendulum in a video earlier a couple days ago, we know that when we release it, it just swings back and forth. And this is because of conservation of mechanical energy. So when it's at the highest point in its swing, because it's higher up in the air, it has all gravitational potential energy. And if all of the energy is gravitational potential energy, it can't have any kinetic energy. And so when it's at its highest point, it stops moving. Then as it falls down and gets lower and lower and lower into its curve, let me see if I can get there. So when it's down here, now it is lower, so it has less gravitational potential energy, but it's still got to have the same total energy. And so it's going to be moving fastest at the bottom when it has the smallest amount of potential energy, because that's where all of that energy has been converted into kinetic energy. So as it falls down, its potential energy converts into kinetic energy, so it gets faster and faster and faster as it gets to the bottom. Its fastest point is when it's at the lowest, and then as it goes back up, it will slow down as it gets higher and higher and higher as that kinetic energy converts into potential energy until eventually it's all potential energy and it stops at our highest point, and then it just repeats back and forth. And in this case, we could imagine describing its position just from left to right on the screen. And so we could measure exactly what its position is at each point. And because the pendulum system has sort of this defined position it's going to be in based on the angle of the string, we would know that if, for example, we're at this position here, that means that it's going to have a certain amount of potential energy based on the height it's going to be at because of the pendulum string when we get to this position. If we go back, to some other position over here, now it's going to have a different potential energy, but again, it's well defined just based on where we are. So we could make a map of the position from left to right and the potential energy we get at that time. Another one that we could have that would do the same sort of thing is if we had a little, like a curve, we have a curved track here, but this would also work if you just had like a bowl and you set a marble on the inside of it and you just let it roll back and forth. So we see what that looks like. It just rolls back and forth. And this actually works just like the pendulum. When it's at its highest point, it's all gravitational potential energy. When it gets down to the lowest point, that gravitational potential energy is converted into kinetic energy, and so it's going the fastest at the bottom and the slowest at the top. But the total energy, the total mechanical energy, has to be the same the entire time. And so we can define exactly what its potential energy is at any point from left to right, just based on what the height of the track is. And since we know that the total energy stays the same, we could also figure out what its kinetic energy has to be at any point. We can do that with the pendulum as well. So we can make this map of its potential energy at any point based on the height, and we also, if we knew where it started from, we can figure out its kinetic energy. Another one that's a little different is if we have a spring with a mass attached to it on a frictionless surface. And so if we take and pull the mass, so if we take and pull the mass out to one side and then release it, it'll bounce back and forth like this. And so we know the reason this works is because of Hooke's law. So when we pull it out to the side, we are storing potential energy inside the spring. And so then if we release it from this position, if it's at rest right now, it's all got potential, it's all elastic or spring potential energy. It's got no kinetic energy. And then when we release it, it's going to go in the opposite direction, and it's going to bounce back and forth. When it gets to, let me let's see if I can. So we release it from here. Around the middle of its back and forth motion is going to be where it's got the most kinetic energy, or the middle of its motion is going to be where it has the most kinetic energy. This is when the spring has returned to equilibrium. We know when the spring is back in its equilibrium position, that means that it doesn't have any potential energy, so all of the energy in the system has to be kinetic energy, so it's going to be going the fastest when it's in the middle. But of course, since it was moving to the left, it's going to keep on going to the left. And as that happens, the spring is going to compress, meaning that the potential energy inside the spring is going to increase. We're going to have that elastic or spring potential energy. Of course, as that potential energy increases, that means the kinetic energy has to decrease, and so the block slows down until it gets to the farthest point on the left. At that point, the force from the spring is trying to push it back to the right, and once it is stopped, it'll start moving to the right. And then all of that potential energy in the spring is going to get released and put into the block and start pushing it to the right. So it's going to get faster and faster and faster. Once it gets back to the middle, back to our equilibrium position, it's going to be at its maximum speed again because we're back at equilibrium, so all the potential energy has been converted to kinetic energy. And then, of course, it keeps on moving to the right until it reaches its maximum position out here, where all of the energy is back in elastic potential from our stretched spring, and the kinetic energy is zero. And so this just moves back and forth, very similar to the pendulum or the marble rolling up and down in the bowl. And it's just a system that's constantly converting back and forth between kinetic energy and potential energy. And just like the pendulum or just like the marble in the bowl, we can, if we know what our positions are, along our side-to-side x-axis, we're going to know exactly how much the spring is compressed when the object is at each one of those positions, and so we could figure out exactly what the potential energy has to be at each one of those positions, and so we could make a map or a graph of what the potential energy has to be at each position. And then there are more complicated examples we could look at. Here, we have a spring, but it's hanging vertically. And so what we're going to do is take and pull the spring down, and we're going to see it oscillate just like any other system. So let's get going here. So you can see it's bouncing up and down. We know at the very top and at the very bottom it has no kinetic energy because it stops moving up and it stops moving down. And so it's got to be converting between some kind of potential energy and some kind of kinetic, between potential energy and kinetic energy. What's more complicated about this one is we're dealing with both elastic or spring potential energy from the spring, but also gravitational potential energy. And so at the highest point, it has mostly gravitational potential energy, maybe a little elastic potential energy, but it's mostly gravitational potential energy. And then as the object falls, it loses gravitational potential energy, but the spring stretches out, and so it's gaining elastic or spring potential energy. But it turns out that it loses the gravitational potential energy, at least at first, faster than the spring gains energy. And so that extra energy has to become kinetic energy because the total energy of the system has to stay the same. And so if the energy gets lost from gravitational potential and it can't get converted into elastic quick enough, the object's going to speed up. But once we get way down to the bottom of our swing, the spring has stretched out enough that we now have a large amount of elastic potential energy, and pretty much all the energy is going to be elastic potential energy at this point. You can think of if this is our height, if we define this as height 0, then all of the energy is elastic potential energy, which means that we can't have any kinetic energy anymore. And so again, if our kinetic energy is 0, the object stops, and so we can have this system bouncing up and down, converting in between different types of potential energy with any energy that isn't currently being stored as potential energy being kinetic energy. And so again, we could make a map here. We would measure the position vertically instead. But at each position, there's going to be a certain defined height that the object is going to have and a certain defined amount of stretch that the spring is going to have. And so we could calculate the exact amount of potential energy that goes with each position. We could make a graph or a little map of the potential energy as a function of that position. And we know that any energy that's left over that isn't potential energy has to be kinetic energy. So what we're going to do today is look at what would some of those graphs look like for any one of these systems or any other system where we're converting in between potential and kinetic energy, and how can we use that graph to both understand what the system is doing, but also to figure out, how fast is the object going and how is it going to behave? Is it going to oscillate back and forth like these, or is it going to do something else? And it turns out we can figure out all of that information, including whether or not it's going to oscillate back and forth, from the shape of the graphs that we're going to look at.